Those of you doing the iBooks and the apps and the websites, I already have a video of this. Should be in the Dropbox. It's just labeled Precession. First, let me explain what Precession is and show you how this works. Now look, if I tie this rope onto this wheel, and I try to pick this up by the rope, it's not balanced. And this is just going to fall over. I don't want to let go. I don't want to break it and drop it here. It's actually Mr. Rosen's. So anyway, I don't want to face Tom and Steve there. So anyway, if I try to pick it up, it's going to fall over, right? But watch what happens now when I spin it. Because it turns out when something is spinning, and let's face it, everything in space is spinning. Planets, stars, galaxies. Forces are created, forces are generated that you don't expect. When I used to teach physics, I kind of explained it to the kids like, you know what, when you first learn physics in high school, almost all of it's common sense. You know, you push something with more force and it accelerates more. It's common sense. But the deeper you get into physics, the more you leave common sense behind. Until eventually you get to quantum physics and it's complete insanity. Okay? This is where you start leaving common sense behind. Watch this now. Get it going fast enough and look at this. It does not fall over. It doesn't fall. There are forces being created. The torque of gravity is producing a torque that affects the angular velocity, delta omega, the change. There's a change in the angular velocity. What else is happening? Not only does it not fall over, what is it doing? I mean, why the heck is it doing that? Right? Isn't that strange? That there would just be a force to make it go in a circle like that? That's not something you would predict. That's not something you would expect. That is called precession. Now, in a minute, after the lecture, I'm going to come around the room and let you feel these forces if you want. This is heavy, so hang on to it tight. But just try to move it around with your arm and you will feel it working against you. Now, we use that all the time, whether we realize it or not. For example, try to balance on a bicycle sometime without moving. You get on a bicycle and put your feet up on the pedals and see how long you can balance there. Not for long. But as soon as you start to move, it becomes very easy, right, to balance on a bicycle. Again, it's those forces of the spinning wheels that are helping you balance. They help you stay up. They prevent you from falling over. NASA uses this in something called the Hubble Space Telescope. The Hubble telescope actually has 6 gyroscopes. What's a gyroscope? It's a spinning wheel. It has 6 gyroscopes that help it balance, because the Hubble has to, pinpoint these objects, these galaxies, millions and billions of light years away. It has to remain incredibly stable as it's going around the Earth at tens of thousands of miles per hour. So it has 6 gyroscopes on board to help it balance. They do the same thing in the cruise missiles and things like that, have gyroscopes that keep them balanced. Okay, so we actually use this as a practical matter, precession. Now for this class, astronomy, how does this relate to space? Well, as I mentioned, everything in space is spinning, including the Earth. So, what does a top do? When a top is spinning, what does it start to do? It wobbles. Guys, when I say the word precession, the first word I want to pop in your mind is wobble. If you're doing the iBooks and the glossary, you could write down precession as the wobble of a spinning object. That'd be a good definition. The wobble of a spinning object. The Earth does wobble. Very slowly. You ready for this? For the Earth to wobble one time on its axis takes 26,000 years. That's a slow wobble. 26,000 years. This is not exactly something that's going to mess up your weekend plans. Okay? Not something you have to account for, all right? Not something that's going to bother you during your lifetime, but I think it's an interesting thing. Now, what would it affect? Well, over enough time, there are a couple things it would affect. For example, right now, let's say we know the Earth is tilted. How much is the Earth tilted by? 23.5 degrees. 23.5. Let's say the sun is over here, and this is June. the month of June, and we're tilted towards the sun in June. But here's what's going to happen. Over enough time, the Earth's axis is going to stay at 23.5, but it's going to wobble so that eventually, if we kept the same calendar, the same months, in June, by the time we wobble over here, June will be winter. Let's say it that way. June will be winter. June will be a winter month. June will be in every season eventually. It will be a fall month. It'll be a winter month. Question, how long will it take June to go from being a summer month to being a winter month?
13,000.
Nice. Half a wobble. 13,000 years. And in 26,000 years, it'll be right back to where it started. So a little tidbit, a little trivia kind of, but it's kind of interesting. How about this? One other thing that would change is the North Star. I think this is a very interesting map here. Check this out. Check this out. I think I'm going to have to shut off the light here for the camera to be able to pick this up better. So look at this map here. Very interesting map. If the Earth was not tilted at all, our axis would point straight up where this X is at, and we would be right in the middle of Draco there. Okay? That would be north for us. But we are tilted. And we're tilted to where the yellow circle is at. And the yellow circle actually represents our complete wobble over 26,000 years. Let's take a look at where we're at now. Here's 1 AD. Every tick mark is 1,000 years. 1,000 AD. 2,000 AD, we're just past that. And look at that. Right now in history, the star Polaris is right on the line. What a great North Star Polaris is. That's perfect. And it's a pretty bright star. So it's right on the line. It's pretty bright. That's what you want from a North Star. But let's go back in time. Let's go back in history. Let's go back to 1 AD. The height of the Roman Empire. Well, guess what? I don't see any bright stars near the yellow line. Isn't that interesting? The Romans, when they're going north, let's say, to invade Gaul and Germania, they're conquering lands to the north, they don't have a North Star to help guide them. There is no North Star for the ancient Romans. Let's go further back in time. Look at this. 1000 BC, 2000 BC, almost 3000 BC. Oh, look, another star now is right on the line, but it's a different star, Thuban, which is the tail end of Draco the dragon. So when the Egyptians were building the pyramids, they had a North Star, but it was a different North Star than we have. Thuban. Isn't that interesting? Let's go into the future. Eventually, maybe in the year 4000, it looks like this little star from Cepheus might be called the North Star, but it's not a bright star. It's not going to be a great North Star because it's not all that bright. Later, look at this, long stretches, 8000 AD, 9000, there's just going to be no North Star. I'm not looking forward to those astronomy nights. All right. And then eventually now, in about 10,000, we may use Deneb as a North Star. Maybe this star here. Vega, which is super bright. That may be our North Star in the year 14,000. And then there's a huge stretch of thousands of years that go by with no North Star until, look at that. Yeah, Thuban will get its chance again to reign as the North Star. Interesting, right? Yes?
Do you know if it's true, like, in the year 2200, there's going to be 2 moons? Because I saw something on Twitter, like...
Nah, I've never heard anything like that. I don't know why I'd have to investigate why they would even suggest that. I have no idea, but that doesn't sound very legit, to be honest. All right.
It's some kind of, like, meteorite or something.
All right. Short lecture today. We're going to do one more small topic here. Again, something that's not exactly going to affect your life a whole lot, but something I think that's interesting. It's something that I think you've never probably learned before in middle school or 9th grade earth science or wherever. How long does it take the Earth to spin on its axis? 24 hours? Well, actually, it takes the Earth 23 hours and 56 minutes to spin one time on its axis. That is called a sidereal day. Make a note of that, please. Those of you not taking extra notes are going to regret it. 23 hours and 56 minutes. That is called a sidereal day. Is that what we base our time on? 23 hour and 56 minute days? No. We base it on what? Yes, what we call a solar day, which is 24 hours. Because remember, when we're setting up time, when ancient people are setting up time, they're basing it on the sun. And they're using simple things like a sundial and the position of the sun in the sky. And they just divide up the time into equal increments, and we call them hours. But they're basing it on the sun. And they don't really know or understand that it actually takes the Earth a little bit less time to actually spin on its axis. Let me explain why. Take a close look here. You're standing at point A on the Earth. It's noontime. The sun, as you're standing right here, is directly over your head. That's noon. You spin around on the axis until you get to this line. Now, here's what I'm saying. Look at my meter stick. Look at it here. Look at it here. Same angle, right? Do you see that I've made one complete spin? Now that takes 23 hours and 56 minutes to make that one complete spin. But question, when I spin around to the same angle again, is it noontime? No, it is not. The sun is not directly overhead. I have to spin a little bit longer to get the sun directly overhead. How much extra do I have to spin? 4 minutes. You got it. Why is there a difference? Why do we have to spend that extra 4 minutes? What is happening? What's happening while we spin on our axis? Thank you. We're revolving around the sun at the same time. You see what's happening? We move. If we just sat in space and didn't go around the sun, then it would take 23 hours and 56 minutes, and that would be that. But that's not what's happening. We are actually going about 1 degree of our circle around the sun. We're going about 1 degree of that, and that changes the angle to where we have to spend an extra 4 minutes to get all lined up. Any questions on that? I know that's a little tricky. We'll be doing this again with the months. There's a similar thing with the months that we'll learn very soon. Sidereal day, 23 hours and 56 minutes. That's how long we actually spin on our axis. But because we're also going around the sun at the same time, our solar day from noon to noon ends up being 24 hours. And that's what we base our time on.